Let's do this problem. Let's start off with this problem over here. We have a field and the surface bounded by the cylinder y squared plus z squared is equal to 1, and then the planes, x is equal to -1, x is equal to 2. So your cylinder goes like this, and then you have a plane over here in front, x is equal to 2, and then the plane here in the back, x is equal to -1. So if you were to do this directly, finding the line integral or finding the flux integral, you would need to take 3 surfaces, S1, S2, and S3, and then run this field through the flux over each of those surfaces individually, so you'll have 3 flux integrals to compute. But since this is a closed surface, that means there's a region, a solid inside that we can define that is well defined, and that's what we'll have for E. Okay? So part of this theorem tells us that we also transform our field into the div of that field. So we want to take the div of that field, and that's what we're going to put inside of the triple integral. So let's compute the div of f. And the result is a vector field or a scalar function? Scalar function. So we take the derivative of each component with respect to whatever that component spot is. So derivative of this with respect to x, that's 3y squared. Derivative of the second one with respect to y, no contribution. And then derivative of the last one with respect to z, 3z squared. So that's our vector field now transformed into a scalar function, and that's the div. And then if we take a look at our solid E, this is our solid E. We can just get this set up and then think about how we would do this as a triple integral. So we got 3y squared plus 3z squared dv. Say it again? So I probably want to go cylindrical coordinates, but not your standard cylindrical coordinates where the x and y are the cosine and sine thetas. So we have to probably consider the y and z axis to be the cylindrical coordinates. So we're going to go cylindrical on the yz. So that means our x is going to be the another free variable, and then the y and the z will become the r and the theta. And since we are doing just the regular triple integral now, where the orientation doesn't matter, it doesn't matter which one goes with which. And we don't have to check for orientation here anymore. Except for the beginning, I'm assuming that this is a closed surface and the original orientation for the flux is going outward. And so by finding the inside of that surface, then that's the solid that you're going to deal with. So this is your cylindrical coordinate transformation, which means your dv will also change into a dx, dr, d theta with an extra r. And that also probably will mean that y squared plus z squared is going to equal to r squared. Yeah.
When do you know when it has an r
I think you just remember if you're going to go change coordinates after you set up your integral, then when you change your coordinates here, we're explicitly saying we're going in the cylindrical coordinates, so we know that our dv is going to be r dx, dr d theta. So we know that there's going to be an r that goes in here. If we set up our parameterization for a surface integral that uses r embedded in there already, then that r will come out during the cross product. So I guess we should also figure out the limits here, our r limits and theta limits and x limits. So I probably want to do x first. X looks like it's just going to be constant limits from -1 to 2. And then r, this looks like it's a radius 1 cylinder. So let's go from 0 to 1, and then this goes wraps all the way around 0 to 2 pi. So this is 3r squared, and then we have that extra r from the dv. And depending on what we want to integrate with respect to first, if I integrate with respect to x first, I'll have dx from -1 to 2, and then dr from 0 to 1, and then d theta from 0 to 2 pi. So this whole thing is your dv. And it looks like this integral is one of those that you can break up and do things individually. So 0 to 2 pi d theta, and then collect all the r's, put the 3 out here. Integral from 0 to 1 of r cubed dr, and then there's no x's in here. -1 to 2 dx. So if we just do them individually, first integral is 2 pi, second integral is 1/4, r to the 4th over 4, and you put 1 in. And then the last integral is just the length between -1 and 2, which is 3. So I will call this probably 9 over 2. Okay. Pretty easy, huh? All right, let's take a look at a homework problem. Which one? So it's asking us to use Gauss Theorem. Use Gauss's theorem to find this this flux integral, where this is your given field, and S is the top half of the hemisphere, top half of the sphere. Looks like it has radius 2. Note that S is not a closed surface. First compute the integrals S1 and S2, where S1 is a disk oriented downward. Oh, what? Yeah, I haven't done the flashlight problem yet. I was going to do that first. Well, let's do this one first, and then maybe we'll get to the flashlight problem. What flashlight problem? Yeah. All right. So, if you take a look at the divergence theorem, S is the boundary of a surface, boundary surface of a solid E. So this S is necessarily going to have to be a closed surface for it to be a boundary of some solid. Right? If it's not closed, then the solid would ooze out. Come out. Ooze out sounds better. So we have an issue with this surface in that we can't use Gauss's theorem because the surface is open. Right? So we have the sphere, and it's the top half of the sphere. So what they're suggesting is for us to compute this flux, what we're interested in doing is to cover it and then subtract it out. How is that going to be helpful? No, we'll see. Well, first try to imagine doing this directly, doing this line integral directly. The whole point in these integrals is to have an easier integral to compute. And if you imagine doing this directly, this is your vector field, F, and then this is your surface. And so you're going to have to find a parameterization for x, y, and z and plug those values of the parameterization in for x, y, and z here. And it looks like it's going to be a lot of work. So instead, what we're going to do is we're going to cover it with this disk over here. And we're going to look at this disk just to match the normals. If this was going to completely cover the solid now is a hemisphere, we're going to want our orientation to be going downward. And so that's why they suggested that we have a downward orientation for our cover. So what we have essentially is that if we call this first surface S1 and the second surface S2, then we have what? S1 is the hemisphere. Oh. Whatever. Where? All right, fine. Which one is the disk? S1. And the whole thing's S2, so this is S. You happy? So, this is what we want. This is the surface, the hemisphere. And then if we add on the S1, which is the disk, we're going to get a new surface we'll call S2. So this is the flux of this new surface that is now a closed surface. So this closed surface, once we close it, it becomes a boundary of the solid hemisphere that we'll call E. And according to the divergence theorem, this is equal to a triple integral of the solid. Okay? So I'm not putting the stuff that goes in here, but you should know what this is. So this is capital F ds, capital F ds, capital F ds. And this would be the div of F dv. That's when you make the jump from your surface integral to Gauss. So, but keep in mind that this is what we want. So in this long string of inequalities, you'll eventually get what we want is equal to the triple integral minus the flux integral with the disk. Okay? So we're buying into this whole idea of Gauss's just because we're hoping that our computations will be easier. Okay? I don't know if it's worth going through the process of seeing how difficult it is to go through this thing directly. But if you want to try, you can go ahead. So I'll just compute the right-hand side, which means doing the flux integral of the surface should be easy. Let's see how easy that is. Let's do that one first. So we want this computation first. So this is our long, complicated vector field, right? You don't get to take the div of that yet because that's what goes into triple integral. So you need to take that original vector field. And let's find a parameterization for this. You can go directly into the sine and cosine if you want, but I always like to use x and y and then change into polar later on. You might not, because we have the normal vector, right? And so you got a lot of stuff going for you already here. So let's just, I still want to label the way I would like to parameterize this. Let's just call it x equals x, y equals y, and z equals what? It's on the xy plane, right? So already that 0 is going to knock off a lot of things. And if we do the cross product in the vector, we'll see that this is going to be an orientation reversing parameterization, so we just throw a negative sign. Yeah? So phi x, phi y, 1, 0, 0, 0, 1, 0. And when you cross it and you get to the last one, you'll see 0, 0, 1, which is the opposite of which how we want this to be. So we're going to call this ORP and then deal with it with a negative sign. Caesar already said that if this is a downward pointing normal, when you do the surface integral, you're just going to dot this with a normal. And so, first of all, the first two components are 0, and then the third component has a z component, so that's going to go to 0 also. You'll just have a y squared or something, negative y squared. But we'll see that come out of here also. So, we have an ORP with this parameterization, and this is our normal vector. And it looks like in our parameterization we're going to put an x in for x, a y in for y, and a 0 in for z. So our vector field F is going to be 0. There's a 0 in the first component. Sine of z is 0, right? So that's just y cubed over 3. But you know that's not going to matter. And then the last component, there's a z over here that's also 0. And so you just have a y squared. Right? And then you're going to dot that with 0, 0, 1. And so everything's going to disappear except for the y squared. So then your surface integral, your flux integral, is going to now shrink down to a plain old double integral. When we take the dot product of these two things, you just have a y squared, and then you'll have a dA, dx dy, integrated over d, some domain, And the domain here is some circular domain. So now is probably the time I would be interested in going into polar coordinates. So I can complete this integral. And then I would say this is equal to y would be what, r sine theta. So r sine theta, I want to square that. So I want to square this, and then there's going to be the dA, which is going to have a r. dr goes from 0 to 2, I think, 2. And then theta goes from 0 to 2 pi. So I have one of those sine squared things that I have to evaluate. Oh, negative, yeah, the ORP business that we did, which would have come out if you just had this point downward, and then your 1 would be -1 instead of +1. All right. You could separate this. Have you guys done enough of these integrals, or can somebody just punch in the sine squared theta from 0 to 2 pi in their integral? No? No? All right, I'll compute, since I can break this up to 2 different integrals, I'll compute the first one. 0 to 2, that's r cubed dr. It looks like it's going to be r to the 4th over 4, and then 2 to the 4th, 16 over 4, so that's just 4. And then whatever the integral of sine squared theta d theta is. Is it pi? I think you guys should do a little bit of work here, so let you guys figure that out. So somebody said it was pi. I'll believe it until I get the wrong answer. -1. What? All right. Now let's take a look at the other part that we have to compute. So the triple integral, according to Gauss, says that surface integral can buy into a triple integral if you take the div of the original function. So let's do that. So the div of f, it's not a vector, it's a scalar. So take the derivative of the first term with respect to x. It looks like it's going to be z squared. Take the derivative of the second one with respect to y. It'll be y squared. The third one with respect to z, it looks like x squared. Wow, this is like a setup, right? And then our solid E is a solid hemisphere. Hemis. Yeah?
When you do the div and the curl, you have to use rotation formulas.
Yeah. Well, you can find formulas where you can use the find div and the curl using those cylindrical, spherical, but we're not going to go there. In fact, there was this interesting formula that I used to have people derive to go polar coordinates. It's not a div and a curl, but decided to spare you guys the trouble. It was a proof of something, it was a proof of a chain rule that I would go through and not finish in class. And I would take a picture of the work that I did in class, and I would put it on a test and say, here, finish it. No. It was in an actual exam, and people didn't know how to finish it, so I stopped doing that. I thought it was kind of cool, but anyways, we have a part of a sphere for your solid, right? So I think it's natural to go into spherical coordinates for this. This is now a triple integral. We've got x squared plus y squared plus z squared dv. And if you go into spherical coordinates with your solid, this is a solid now, right? So we have rho involved. You know, when we parameterize surfaces, rho was constant because it was just the thickness, or not the thickness, but the surface itself. But here it's solid. And radius is 2, I think, last check. So rho goes from 0 to 2. What's that? And then we have phi and theta, which I hope you hadn't forgotten about. And we're going halfway down, not all the way down, halfway down. So what's our phi going to go from? We're going to stop at pi over 2, and then our theta goes all the way around to 2 pi. And we know that in changing to spherical coordinates, we can say x squared plus y squared plus z squared is all equal to rho squared. So we have rho squared. dv changes into what? Rho squared sine phi, for those people that have it memorized. For those people that don't, just make sure it's in your notes. Rho goes from 0 to 2. Phi goes from 0 to pi over 2. And theta goes from 0 to 2 pi. It's a nice enough integral that we can split up, so let's do that. Let's take the d theta first. There's no thetas in there, so that's just going to be 2 pi. And then we could take the rho. This is rho to the 4th power. So it looks like it's going to be rho to the 5th over 5. Put 2 in, you get 2 to the 5th is what? What? 32? So 32 fifths for that one. And then the last one is integral from 0 to pi over 2 of sine phi d phi. And if you know that the integral from 0 to pi of sine is 2 or 1. I now forgot. So it's 1. So it is. So sine of from 0 to pi is equal to 2. That's the area under one sine curve, right? But I'm going to cut that in half, so that's just 1. So what was it again? This is 2 pi. This is 32 fifths. And this is 1. All right? So, putting it all back together, our original flux integral with the original S. Let's put in all the bells and whistles here. This is equal to the first integral that we calculated, 64 pi over 5 minus, and this has a negative sign built in, so 2084 pi over 5. Yeah? So we successfully covered the open surface to make it a closed surface so that we can, in fact, use Gauss's theorem. We use Gauss's theorem. We traded a difficult flux integral with a simpler flux integral with that surface that we used to cover. And then we use that to subtract out the covered flux integral. We subtract out the thing that we use for its cover to find the original flux of the surface. Okay? Let's see if we got it right. As an instructor, I can put it whenever I want, and it'll be correct. No, I'm just kidding. Looks like it's always right.
All these years.
Okay? So is that good?
That's already a scalar.
It's the flux through that surface. So you have a vector field. You want to measure the flux going through that surface by computing a bunch of dot products with normal vectors. Hmm?
It's pre-scalar.
Pre-scalar. What's that mean?
I mean, you know how to feel.
Remember, we took Stokes' theorem down to 2 dimensions, and what did we found?
Green's theorem.
Green's theorem, right? Can we take this into 2 dimensions? So it's kind of weird to take this down to 2 dimensions since we are talking about a triple integral of a solid here. But let's see what we can do about this. Oh, I don't know if I thought about this enough to be able to do it properly. What if I just put dot, dot, dot here and give you the result? All right, let's say F was just a 2-dimensional vector field, because that's what scaling it down to 2 dimensions would be. So F is just a vector field in 2 dimensions, and let's put 0 in for the z component, and let's see what we get. The div, what happens to the div? Just going to be a, so dp dx plus dq dy. And 0 because there's nothing in the z component, right? And what happens to this flux integral? Can't remember. Let's see if I can take a stab at this. Since the surface, this would only make sense if it was flat on the surface because z is equal to 0. We're going to have to force all the z's to be equal to 0 on your surface. So this would become, I don't know what it's going to become. I think it f dotted the normal ds. How's that helpful? So if this is flat on the plane, then the normal vector has to be the perpendicular vector has to just be going up in the k component, right? Do we want that? Oh, I don't know. I give up. Just going to cheat now. Good thing I get a page of notes on the test, huh? Two pages of notes. So this is at the end of Green's theorem section. Oh, it was close. So I just had to make that surface into a curve somehow. And then it's a div of f. So here's sometimes this is shown with sometimes this is shown with Green's theorem, sometimes this is shown after they do Gauss's theorem, but this is called the divergence theorem on the plane. On the plane in the sense that it is two-dimensional, and we are looking at this as Gauss's theorem, but brought down to 2 dimensions. So there's no official theorem for this, but if we look at the way the progression went, we went from Green's theorem to Stokes' theorem, but Stokes is a higher dimension case of Green's theorem, so we should be able to look at this as a lower dimensional case of Gauss's theorem. So that's just another tie-in with those integrals. Okay. So that last problem, let's go back to this last problem. Yeah, what is this? Yeah, you guys might have to read about that. Let's see if we can find some more other interesting problems. Yeah, I think that's about it. Oh wait, this is the wrong section. Uh-oh, lost my page. So let's see, should we do another one? Hey, that's like number 24 over here. I wonder what's up with that. Maybe we should try to work that out. So clearly this is not a flux integral. Well, I don't know if it's clear, but it doesn't look like a flux integral. It it's a surface integral. So to make it a flux integral, we would dot it with some normal vector, right? Is there any way we can think about dotting this with a normal vector? Or wait, let's put it this way. This is like an algebra question. So this is your resulting yeah, so this is your resulting f dot n. Which is a scalar function, right? Now, if we know that the the surface is a sphere, can we take a stab maybe of what n might be? What is n? I suppose. So if this is your surface, your normal vector is always going to be essentially the same as your position. So if you're at the point x naught, y naught, z naught, then your normal vector is also going to be x naught, y naught, z naught. So it is going to be x, y, z. And this is already a unit vector, so we know that this has to be a unit vector, so we know that this is going to be x, y, z. Right? Agree? Yeah. Then you'd be in trouble. The thing is that spheres and cylinders and maybe even square boxes are like the most popular shapes that people are interested in collecting information about these fluxes anyways. And so they have a lot of little tricks like this. So we still don't know what f is. That's what we're trying to recover. And if we know that n is just x and y and z, then it should be easy to figure out what the original f was, right? Yeah. Thought you had a question. So capital F is equal to what? 2, 2, and z. All right. So this is our, now we can change our surface integral into a flux integral. And this is a closed surface now, the sphere, solid sphere. And according to Mr. Gauss, we can change this into a triple integral of the div of our vector field. So we need to take the div of this. What is it? 0 plus 0 plus 1, which is just 1, right? So this is a triple integral over the solid sphere of 1 dv. What is this equal to? 4/3 pi, and r is the radius of our sphere is what? 1. So it's just 4/3 pi. See, whatever I put in is correct. Special instructor feature. Okay, so it turns out that the div is a really nice, simple sort of derivative that we can use, we can take advantage of, and you're not going to see very many problems like this where you have to kind of go backwards and do an undiv or something. That's like undotting, whatever it is we did. What did we do? Yeah, so we took the dot product of some unknown with some known, and we got an answer. We went backwards to try to figure out what that is. But taking the div of a lot of these vector fields will simplify your vector field a lot, make it into a scalar. And so a lot of times that will come in handy. Okay. Any questions? Just let out a big sigh. Is that, wow. So, I can't find my flashlight. I didn't look for it very hard. I think it just means questions. So, in place of a flashlight, I used a rocket last year. So here's my problem here. I have a rocket made up of three surfaces. The top is a cone, and then I have a washer connecting that cone, and then from the washer I have a cylinder.
You're just like separating out the cone and cylinder?
Yeah. What? Right here. Well, it has to match the radius. The outer radius matches with the cone, and the inner radius matches with the cylinder. So, given a surface like this, I can ask for a couple of questions where you might be interested in using one or the other, or one of those theorems. There's no bottom in this, so if I ask for the flux of a curl of a vector field of this, flux of the curl of the vector field, you would be thinking about Stokes' theorem, flux of the curl of a vector field, okay? Flux of the curl of a vector field, what you would do is you would trade doing the flux of the curl of three surfaces like we have here to just doing the boundary. Since this is an open surface, you're going to look at the boundary and try to parameterize that boundary. Okay? And then I can ask for the regular flux integral. And if you think ahead by looking at that vector field that I would give you, if you think ahead a little bit, you might be interested in covering this up and making it a solid, and then just find the triple integral of that solid, and then subtract out that little bit of the circle that you added on. So that's going to be our exercise for tomorrow. I'll get this a little bit more prepared for you tomorrow, and then you guys will work in groups and try to work through this as an example. So, in terms of getting ready for the test, I've mentioned, whoops. I've mentioned that these 4 review sections would be a good way to start preparing for the test. I would suggest that you study all your quizzes and all your exams. And so your first question will be something that was covered in the first exam. Your second question will be something that was covered in your second exam. And then the rest of the questions will be based on Chapter 16 material. Yeah?
Will we get our Chapter 16 quizzes back?
What quizzes?
The group quiz?
Oh, that.